All right, in this video we're going to look at working backward from the derivative of a natural log. So let's just do a recap and remember what the derivative of a natural log looks like. So if you'll recall from back in the day, which was what, I don't even know how long ago that was, to be honest. If I was going to find the derivative of something like x squared plus 3x plus 1, we found that the derivative of a natural log comes about by taking the inner function, so this is u, the inner function, and that's the denominator. And then the derivative of the inner function, 2x plus 3, that will be the numerator. So that's the derivative of a natural log. And we found the generic formula for that. So we generalized, oops, I'm jumping ahead of myself. If we have the natural log of, if we have the natural log of any function u, and take the derivative of that, we found that the derivative of any natural log with any inner function is u prime over u. Sorry, I'm getting it together. So what that means is, in order to find an antiderivative, we need to make sure that if we've got something in the form of u prime over u, another way to see that is 1 over u times du, or another way to write that is du over u. The antiderivative of any of those in this form is the natural log of u plus some constant. So remember, in the last chapter I said that there is no such thing as the derivative of a fraction. Well, there is, as long as the fraction is in this form u prime over u. And you'll see later on in this chapter there is another form of a fraction that we can also integrate. But they've got to be in this special form. If the fraction is not in the form of u prime over u, or can't easily be made in the form of u prime over u, what that means then is that we have to find another way to integrate. Okay, let's do an example. So if we look at, today's going to be mostly examples and just looking at different forms. So if we look at an example, I'll do the first one with you and I'm going to let you then try the second one. If we look at a problem like this, now mostly what we've done in the past is we've said, well, let's just bring that denominator up to the top. There's a couple of things that can go wrong with that. First of all, you have to think about the fact that 2 is also in the denominator. So we can get around that though. I mean, if we rewrote this as 1/2 times 1 over x dx. And then that 1/2 is just a coefficient or a constant. That 1/2 can easily be brought out of the integral. Now, we've done this, and you've done this a lot, and this was a valid, and it's mostly a valid method, is bringing that x up to the top. So let's watch what happens when we do that. So if we bring that x up to the top, this becomes x to the -1 dx. Great. Now, if we try to work backward from the power rule, so if we work backward from the power rule, we would say, well, we need to add 1 to the exponent. So now that exponent is 0. And then we would take the coefficient of x and divide it by that exponent. Divide by 0. But dividing by 0 in this case makes this entire, well, in any case, dividing by 0 makes this entire thing undefined. So the method that we have been using, where we try to work backward from the power rule, doesn't work in this situation, because -1 plus 1 is 0, dividing by 0 is undefined. So this method it doesn't work in this situation. And I hope that when you get yourself into a situation like this, you think about this problem right here. So I'm going to write it back again as 1/2 the antiderivative of 1 over x dx. Because now I'm going to think about the fact that this is a fraction, and I'm wondering if this fraction is in the form of u prime over u. If it were, then I would look at u being the denominator. U is x, u prime or du, however you, du is 1 dx. So if I rewrite this integral then, I get 1/2. The 1 dx becomes the du. X is u. Yes, this is absolutely in the form of u prime over u, or du over u. So I know that this is 1/2 the natural log of u plus a constant. And in our case, u was x. Notice the absolute values. Got to make sure that we're only looking at the positive values of x. Those are the only values that work with a natural log. A natural log can only output a positive value. Okay, let's try a different example. I'm going to let you try this one. Number 2, oh, that's a good color, I like that one. I want you to try this, please. 5x over x squared plus 5 dx. Okay, pause this. I want you to go give it a try and come back. Okay, I hope that you tried it. So in this case, bringing the x squared plus 5 up to the top is not going to help us. I'm going to do it anyway because people love to do this. For some reason, they can't get past moving that denominator up to the top. But if I try that, that gives me a bit of an issue because I cannot distribute the 5x in. If I try, this is 5x to the first, and this whole thing is to the negative first power. I cannot distribute the negative 1 in here because the addition keeps that from happening. So really bringing that x squared plus 5 up to the numerator and making it to the negative 1 power doesn't give us any algebraic advantage. Okay, so since that doesn't work, I'm going to think about the fact that this is a fraction, and I'm wondering if it's in u prime over u or du over u form. Okay, so I'm going to get rid of this because that didn't work. And if I do think about this as a natural log, I would let u be the denominator then, x squared plus 5. The derivative is 2x dx. So what that means is, and you can do this however you're thinking about it, however you thought about it in the last chapter, that's great. But what I'm going to do is multiply both sides of this by 5/2. So 5/2 du, and if I multiply the right side by 5/2, I get 5x dx, which is exactly what I need. Okay, now I can make my little u substitution. This 5x dx becomes 5/2 du. The denominator is just u. That 5/2 is a coefficient or just a constant, so I can bring that outside of the integral. And now I've got this nice, straightforward du over u. I know the antiderivative of that is the natural log of u. And in our case, u is x squared plus 5 plus a constant. All right, now let's go on to another example. Let's try number 3, sorry. Yeah, 1, 2, and then 3, correct? All right, let's try this one. This one's going to be a little bit tricky. We've got 2x over x plus 1 dx. Okay, pause. Go give it a try. Okay, welcome back. Since we have x plus 1 in the denominator, moving that up to the numerator is the same issue we had on the last problem. X plus 1 to the negative 1 doesn't help us at all. Okay, so I'm going to think about u being the denominator, u equals x plus 1, du equals dx. If I make those substitutions, I've got 2x over u du, but we still have an x. So this was that method that we used in the last unit, where we can rewrite x as a function of u. X is equal to u minus 1. And if I do it that way, but that's not in the form of u prime over u or du over u. So don't forget about things that we've done in the past. These things still keep coming back. So all of the methods we've used in the last unit are still methods you're going to need to think about in this unit as well, and every unit from here on. So if I rewrite this then, because we've got 2u minus 2, this is not in the form of du over u either. So now we think back to what we were doing before. U is the denominator, so I can bring that up because that's just one single term. Now I can write that as u to the negative 1 because it's just one single term. It's not x plus 1 or, some binomial. Now I can distribute the u to the negative 1 in here, and I end up with 2, just 2, because u to the first times u to the negative first is u to the 0, and then 2 times u to the negative 1. Okay. Now if I find the antiderivative, I'm really thinking about these as two separate problems. I'm getting lazy with my du by not writing it. The antiderivative of 2 is just 2u, not x, because we're dealing with u's right now. We've made the u substitution. And this one was that same problem we had before. If I add 1 to this, that makes that exponent 0, and I can't divide by 0. So let's think about it in a different way. This is 1 over u. I can bring that constant out in front. And I know that 1 over u is in the form of u prime over u, or du over u. So I can rewrite this as 2u minus 2 times the natural log of u plus c. Now if I wasn't lazy, I would have had my du here, or I could have written it as du over u if I wasn't lazy. And that's probably the more formal way that you should be doing it, but mathematicians are inherently lazy. Okay, now I'm going to replace u with x plus 1. Like so. Okay, let's see, what if we find the antiderivative of tangent? Whoa, not in the highlighter. Let's use a different color for trig. Find the antiderivative of tangent x. I'm going to let you pause. I'm going to let you go try. Okay, now let's take a look at this. So if we have tangent x, we don't know the antiderivative of tangent. We know the antiderivative of secant squared is tangent, but we haven't looked at the antiderivative of tangent. So if we rewrite tangent as sine x over cosine x, now we've got this in terms of a fraction. And now we have a way to think about finding antiderivatives of fractions. So let's see if this is in the form of u prime over u. If we let u equal the cosine of x, then du is negative sine x. So yeah, pretty close. So if I make this instead negative du over u, now we've got what we're looking for. So now we can find the antiderivative of tangent. It's the negative natural log of u, and in this case, u is the cosine of x, plus a constant. Okay, let's do one last problem. Ooh, that is a horrible highlight color. Let's find something a little bit brighter. I wouldn't say that's perfect, but it's not bad. Okay, let's do one last type of problem. Actually, I'm going to do two different types of problems. I'm going to do this one first. I'm just going to do this one with you. We've got 1, let's evaluate from e to e squared, and we have 1 over x times the natural log of x. Things are getting tricky now. You're going to have to get pretty creative with some of these things. Because right now, I mean, if u is the denominator, then du is, we're going to need to use the chain rule, or the product rule. And definitely using the product rule in this will not give me 1 as a derivative. Okay, so I'm going to have to think about this a little different. I'm not sure if this is in the form of u prime over u yet. But let me rewrite this for you, because this is kind of one of those magic things that if you don't see it once, you wouldn't think to even try it. If I rewrote this as 1 over x times 1 over the natural log of x. And even though this is not a really nice way to write a fraction, I'm going to do it anyway. So if I rewrote it again, 1 over x times 1 over the natural log of x, I can write it as this. And the reason I did that is because now it kind of looks like this might be, you know, it's like more of a fraction type thing. So if I let u equal the natural log of x, then du is 1 over x. So now by manipulating, rewriting this fraction, I wrote it in the form of u prime over u, or du over u. Okay, so I can say now that this is definitely the derivative on the top. 1 over x dx is the derivative. So this is the natural log of u, the natural log of the natural log of x. Crazy. And don't forget, this is a definite integral, so we still need to evaluate it from e to e squared. All right, I'm going to plug in e squared first. I'm going to leave myself a little bit more space. The natural log of the natural log of e squared minus the natural log of the natural log of e. Crazy. Let's think this one through. So on the right side, it's a little bit easier. I know here the natural log of e is 1. And the natural log of 1 is 0, because e to the 0 power would equal 1. So this whole thing becomes 0. Okay, now let's look at this other one. We've got some properties of exponents we can use here. So first of all, we can take this exponent off the log and write it as a coefficient. That's going to help you see some things a little bit better. So now this is 2 times the natural log of e. Well, we know the natural log of e is 1. 1 times 2 is 2. And then the natural log of 2 is not something that is really on my radar. So this was 1, and then 1 times 2 is 2. I don't know what the natural log of 2 is, so we'll just leave it as the natural log of 2. All right, last style. This one's funky, but kind of cool at the same time. What number am I on? 6? What color are you guys thinking? Let's do a nice orange color. We're on number 6. This is x squared plus x plus 1 over x squared plus 1. If I let u equal the denominator, du is 2x dx. And there is no amount of constants I could multiply 2x by that will give me that numerator, x squared plus x plus 1. So instead, what we're going to do is long division. I know, you're excited about it. I'm going to divide the denominator into the numerator. So if I've got x squared plus 1, and I'm going to divide that into x squared plus x plus 1, I know that I'm going to put, you know what, I'm going to leave kind of I'm going to take into account that my x squared plus 1 in the denominator is missing that x term. So I want to put that placeholder in there because it's going to help me match things up as we go along. You'll see what I mean in just a second. So x squared times 1 is x squared. 1 times 0x is 0x, and 1 times 1 is 1. Okay, now if I look at these x terms, I need to make sure they match. So I need it to equal 1x, so I need one more x here. But there's nothing that I can multiply x squared that is rational that will equal x. So this x is part of my remainder. Now I need to check in with my constants and make sure I've got enough there. I have 1 for a constant, and I need to make sure that it equals 1. So I don't need anything here. So what that means is that this x is the remainder. Okay, if I rewrite this, then this becomes, I'm going to start out like this, x squared plus x plus 1 over x squared plus 1 dx. When I did that long division, I ended up with this 1 whole time. So x squared plus 1 went into the numerator 1 whole time. That's what this was. Plus I had a remainder of x. So it's plus x over x squared plus 1. Okay, this looks like it might be a little bit more manageable. If I find the antiderivative of each part separately, there are dx's on both of these. The antiderivative of 1, we're all still in terms of x, is x. For this one here, I see that it's in fraction form. I'm going to move things over a little bit so I have some space. I see that it's in fraction form, so I'm going to check to see if this is in the form of u prime over u. So if I let u equal x squared plus 1, du is 2x dx. So yeah, it's pretty close if I just multiply by 1/2. So I end up with 1/2 du over u. If I pull that 1/2 out, now I can say that's the natural log. So it's x plus 1/2 the natural log of u, which was x squared plus 1, plus a constant. So many ways now. We're starting to get so many different ways to find an antiderivative. And there's more to come.